Hello everyone, I am Najme Nazari from the University of California, Davis. I am a member of ASIC Research Lab with the supervision of Dr. Human Homayun. This course development curriculum is funded by Intel Corporation. In this talk, I will be giving you an overview on performance analysis of computing system. This is the fourth video in a series of training modules that would explain how to design hardware accelerator using DPC++ on Intel DevCloud. This slide shows the outline of my talk. After the introduction, I will talk about the performance analysis methodology, metrics, evaluation techniques, workloads, visualization, and finally, tools. Let's start with the introduction. The use of computers on a regular basis in our life is very important. Technically, in daily life, computer is used to convert raw facts and data into meaningful information and knowledge. You can understand and analyze the importance of computers by seeing a revolution in online business, online education, online communication, and internet banking. To store, access, manipulate, calculate, analyze data and information, we use hardware device and software applications. All our daily life activities are based on such online service and products. Ignoring performance in safety-critical system can lead to catastrophes such as what happened for Space Shuttle Challenger. In computer system, we have different domains. System can be an individual software application, it can be a hardware device, or we can have a distributed system, which is a group of computes connected to each other. Generally, performance is the amount of work accomplished by a system. In a computing system, performance analysis means to analyze and measure the accuracy, efficiency, and speed of executing computer program in order to enhance the performance. By using the information provided from performance analysis, we can design a system with higher performance and lower cost. It also helps us to be ensured that system is working as it is designed for. Performance analysis can be used to solve many problems when we want to design or select a system. One of the most usage of performance analysis is in system tuning. When a system has many parameters, determining the optimal value of those parameters cannot be done in designing phase, as they may be dependent to the environment of system. Therefore, we need the performance analysis to find the optimal values. Moreover, we can find the bottleneck of system. For example, it can answer following questions. Does the system need more CPU, memory, or storage? By having this information in hand, we can perform the capacity planning in data centers. And for example, predict how much more computing resources for new users. All this information can be gathered by doing the performance analysis. Other than that mentioned use cases of performance analysis, we can use it for finding metrics that make sense. For example, most of the time we are facing ratio games in data analysis. It can also be used to find the performance requirements of a system, and it's pretty important for many applications. Eventually, when we can use performance analysis to compare two or more systems. For example, when we want to select a better system, we have to do a performance analysis. To perform performance analysis, first you have to define your system. Then determine a metric that you want to analyze, and based on that, select an appropriate workload and evaluation technique. Run your experiments and perform the system monitoring and measurements. If you need, you do simulation. Based on the result that you get from the system, you can tune your experiments. When all the data is collected, you should use a proper statistical technique to analyze your data. Finally, you should present the result of your analysis in a meaningful manner. Now we talk about performance analysis methodology. Let's define common term first. System. System is any collection of a hardware, software, or a firmware. Consider that we want to analyze the storage system of a computer. Then the hard disk is our system. Metric. Metric is the criteria that we want to use for evaluating the system. In our storage example, the performance metric of the hard disk is the amount of data that we can transfer in a second. Workloads. Workload is the input to the system to evaluate the system. In our example, the workload should be big enough to stress the system. In this slide, you can see the system under test. Sometimes we only want to test just a component of the system. To run the experiments, we input the workload to the system and monitor the output. The metric for the evaluation is always a function of input or output, or one of the parameters of the system. It is important to know exactly which part of the system will be evaluated and know what would be the expected outcome of the system. Then, based on this information, we can select a metric. Each system has one or more parameters that we can tune. We have to select which parameter is more important or at least available, and then we can determine the workload and inputs. To evaluate and run experiments, we should select a correct set of tools for monitoring and measurement. When the workload is selected, the experiments can be performed. Characterizing the workload is the most time-consuming part of the performance analysis. To reduce the time of experiments, we can explore the design space or remove unnecessary or redundant experiments. For example, reduce the input size or remove unimportant parameters from consideration. When the measurement is done, we should analyze the results. To analyze the data, selecting an appropriate technique is important. The work is not finished here. The next task is visualization of results, as it can give better insight. Based on the finding from experiment, we can refine the process and repeat measurements and until get the desired results. This graph shows the process of performance analysis. As you can see, after defining the system and setting goals, we can perform the evaluation on a prototype devices or on a simulator or even the theoretical model of the system. After measurements, we should analyze the data and present the results. Metrics. From any system, we expect an output. Based on the functionality of system, we can select a metric to evaluate the performance of system. If the system outputs the correct results, then we can select metrics related to the speed of system. For example, how fast the system can produce the results. If the system did not produce the correct results, then we should consider metrics related to the reliability of system. When the output is not correct, it is not important how fast it can be generated. When the system is not able to respond to the input or generate any output, then we should look at availability metrics. When we use the term performance, in 4 different ways we can interpret it. The first one is responsiveness, which is the amount of time that it takes for the system to generate the output correspond to its input. The example is latency. Productivity, which is the rate of generating outputs or rate of finishing the request. The example is throughput. Utilization, which is the amount of load on the system resources. The example is CPU utilization. Fairness, it shows how fair their users are treated. If a system is not shared, then the most important metrics are response time and throughput. If the system is shared among many users, then utilization and fairness should be considered as the performance metrics too. When we want to show the timing analysis of a computing system, our assumption about the timing of requests and our expectation about the response of system is as follows. Sometimes the event can happen at the same time or the order of event challenges, but usually it is look like the figure. And based on this timing, we define some metrics. For example, you can see the definition of reaction time and response time in this slide. We can have 2 definitions for response time. The time between when a request is finished by the user and the system starts the response, or when the system ends the response. In this slide, we present some common performance metric definition. Throughput, rate at which requests are served. Nominal capacity or bandwidth, max achievable throughput under ideal workload condition, MIPS. Usable capacity, max throughput without exceeding a response time limit. Knee capacity, throughput at knee of response time divided by throughput curve. Efficiency, usable capacity divided by nominal capacity. Utilization, fraction of time a resource is busy serving requests. Idle time, cost divided performance ratio, cost, computed over a given number of years, performance throughput under a given response time constraint. In many computing systems, the throughput and latency or delay are redundant. So we can introduce a new metric to give us a better understanding, and this new metric is power. We can define it as follows: throughput divided by response time. Let's look at the common graph of response time and throughput. Figure below shows that in most of computing systems, when the load of system increases, the response time increases too, and it is not good. Figure above shows the throughput of system that by increasing the load, first the throughput increases. It is a good sign, and we want always to use the maximum capacity of system. But by increasing the load from some point, the throughput reduces, and it shows that the system is not able to handle the inputs anymore. This point is the usable capacity of system. From architecture point of view, the memory system is responsible for a large fraction of overall system power and performance. Today, more processing cores are sharing the memory, and therefore it increases the demand for memory capacity and bandwidth. On the application front, most of workloads, such as machine learning applications, are expected to be memory intensive. Besides, we always expect more from the memory. We want zero latency and infinite bandwidth, infinite capacity, all at zero cost. In this slide, I briefly introduce DRAM frequency and channel. This table shows an example of DDR3 DRAM. When I say DRAM frequency, I mean the front side bus frequency. Actually, this number is double of actual bus frequency because of dual data rate. And also, in DDR3, the bus frequency is 4 times of cell array frequency. The right figure shows a dual channel memory system. Actually, I want to say that the number of channel is not equal to the number of DIM, dual inline memory modules. The number of channels depends on the configuration of memory module on memory slots. And the goal of channel are to increase the bandwidth of access to memory. Memory configuration of a server directly impacts its power and performance. The extent of this impact depends on the performance sensitivity of applications to memory parameters. Based on this equation, the bandwidth of memory is dependent on the configuration of memory like number of channels and frequency. Hence, we evaluate the performance of our workload regarding these memory parameters. Now, let's talk about the metrics related to reliability and availability. Reliability is the probability of error in the output of system. In availability, we have two metrics: mean time to failure and mean time to repair. Mean time to failure, MTTF, is a maintenance metric that measures the average amount of time a non-repairable asset operates before it fails. MTTR, mean time to repair, is the average time it takes to repair a system. The important thing in comparing two or more systems is that the performance metrics that we use have the same definition and have the same base. If we use ratio, then comparing two systems are not as easy as it seems, or even fair. If we use a performance ratios with incomparable bases, then the result may be in favor of one system, and in this scenario, we call it ratio game. We talk about it in the next slide. In general, ratio game happens when two analyses interpret a data in two different ways. Consider that we have two systems A and B. They perform the same task. We measure the throughput of those systems with two different workloads 1 and 2. The result is presented in the table. In your opinion, which of those systems is better on average? If we just calculate the average of throughput of those systems on two workloads, we can say that those systems are equal on average. But what happens if we consider the system B as the baseline and then normalize the result of A? In that case, if we calculate the average of normalized throughputs, then we will see that system A outperforms system B. Similar conclusion if we set the system A as the baseline. So considering ratio game is very important when we want to compare the performance of system. Okay, now I will talk about evaluation techniques. There are 4 techniques to evaluate a system. The most reliable technique is to trace a real system in its operation. However, it is the hardest one and very costly because there are many restrictions in real scenario. The other technique is that measuring a prototype. Using the prototype has lower risk and higher degree of freedom, but still it's costly. The cheapest way to evaluate the performance is to use simulation. However, it does not let us consider all corner cases. And the latest technique is to use the model of system which may have the lowest accuracy. When we want to trace a real system, we need to get the approval of operators. It has many advantages, such as giving us the highest accuracy, but we don't have lots of control over parameters or workloads. We also cannot test the system with unknown or unseen workloads and conditions. Therefore, it does not provide useful insight for future design. The benefit of measuring the prototype is that it does not interfere with serving the user requests, and therefore it is low overhead. This approach of performance analysis is useful for tuning the system parameters and to find the best workload for the system. In this approach, we have more control over the system parameters. Using simulation approach requires a simulator, and developing a simulator requires programming skills. Moreover, to increase the accuracy of simulation, we should consider many details. Simulation helps us to evaluate all parameters of system and tune them accordingly. We can use simulator to check the future system design need. As we may not be able to consider all corner cases and details in the simulation, the accuracy of result is not as high as a real device. In system modeling, we use probabilistic and statistical modeling. Most of the time, we have to consider unrealistic assumptions to reduce the complexity of design. It is the easiest way to evaluate the functionality of system. However, the result would not be accurate. Let's look at the 3 rules of validation. The first one, don't trust the results of a simulation model until they have been validated by analytical modeling or measurements. Don't trust the result of an analytical model until they have been validated by a simulation model or measurements. Don't trust the results of measurements until they have been validated by simulation or analytical modeling. Workloads. First, I present the terminology here. A test workload is any workload used in performance analysis. It can be a real workload or a synthetic one. A real workload is a workload that we observe on a system being used for its normal operation. Synthetic workloads are similar to real workloads, but they can be applied repeatedly in a controlled manner. There is no sensitive information in synthetic workload, and they can be modified easily. Benchmark is a group of workloads gathered together for a specific purpose. Selecting a benchmark is important. For example, if you want to analyze the performance of a multi-core system, you should select a benchmark for parallel applications. So you have to consider the following criteria for selecting a proper benchmark. First, the benchmark should be representative. It is better that the benchmark is portable. It should be unbiased and measurable. Scalability and repeatability of benchmark is also important. There are some well-known benchmarks for different domains. For example, HighBench and Big Data Bench are suitable for big data domain. SPEC is a benchmark for a single core processors, and PowerSec is a parallel benchmark for multi-core architecture. CloudSuite is a benchmark for cloud domain. It is important to present the result of performance evaluation in a way that we can infer meaningful information from them. In the next slide, we present how to visualize the data. There are 4 types of variables: qualitative variables that are ordered or unordered, quantitative variables that they can be either discrete or continuous. For example, number of cores of processor is quantitative discrete variable, but the type of application is qualitative unordered. Now, based on the variable type, let's see how to draw a good chart. When you want to draw a chart, make sure that reader requires minimum effort to understand it. Sometimes it is better to use direct labeling instead of using legend boxes because its readers does not require to look for it. Make sure to maximize the information that you can give to reader. For example, use full name and words instead of symbols. It is not a good idea to draw random quantities with showing confidence intervals as it might be confusing. Makes the figure as simple as possible. In drawing a chart, always follow the 3/4 high rule, which says the height to width ratio of chart should be bigger than 3/4. For that purpose, we can use a non-zero origin. The other point is that you should maximize the information-to-ink ratio. It means you have to deliver the information with less ink. Look at the left figure that shows the availability. There are many columns that they are at the same height, and comparing them with eyes is hard. Moreover, we draw a big portion of data which does not give us any useful information. If we draw the unavailability, then we get the left figure that with less ink, we can get much better information. A common mistake in drawing chart is presenting too many alternatives in a single chart. The other mistake is presenting more than 2 Y variables in a single chart. It makes it hard to understand the chart. Another mistake is to use symbols in place of text when you can put the full text. It is very important to prevent using a line chart in place of column chart. It is the most common mistake. Keep in mind that do not use a line chart for unordered categorical variables. Now let's look at some monitoring tools used in computer. A modern hardware looks like this. Your system may have 1, 2, or 4 sockets of processors. Each modern processor is a multi-core CPU, and each core may have 1 or 2 execution threads. Therefore, we can evaluate the hardware from system level to the microarchitecture level. Generally, we can have 2 levels of information extraction, system level and low level. At the system level, we can extract the information of individual components at coarse-grained time span. For example, we can monitor the main memory every second. At the low level, we can extract the information regarding each component at a fine-grained time span. For example, we can look at cache miss rate in 1 microsecond. Popular tools for performance analysis are Intel VTune, Intel Advisor, dstat, Intel PCM, Mika, and perf. dstat is a tool for extracting system-level information on Linux OS. It can monitor virtual memory, network communication, I/O, and storage, and CPU. Perf is a tool that we can use for low-level monitoring, and it reports architecture-dependent metrics of CPU. Intel PCM, Processor Counter Monitor, is an application programming interface API and a set of tools based on the API to monitor performance and energy metrics of Intel processors. Intel PCM can report on-core events too. Mika is a pin tool which allows the user to collect a number of program characteristics such as instruction mix, instruction level parallelism, register traffic, working set size, data stream strides, and branch predictability to quantify runtime program behavior. Mika was developed for microarchitecture independent characterization of application. Intel VTune is a performance analysis for applications and systems. It is useful for find and fix performance bottlenecks. The performance analysis is done by analyzing your code, collecting key profiling data, and presenting its finding through a powerful interface that simplifies interpretation. Intel Advisor is a prototyping tool that allows users to analyze their code and determine the code and benefits of adding various trading models on Intel processors. It can model parallelism using OpenMP Intel thread building blocks. There is a common question that when to use Intel VTune or Advisor. You can use Intel VTune when you want to know what's your cache hit ratio, which loop per function is consuming most time overall. Are you stalling often, IPC? Are you keeping all the thread busy? Are you hitting remote NUMA? When do you maximize your bandwidth? You can use Intel Advisor when you want to know flow of execution, call stacks. What is your vectorization efficiency? Can you safely force vectorization, inlining, data type conversion, and roofline? Thank you for watching. I encourage you to follow up with other videos, and there will be also a GitHub repository that provides all the codes.